Why traditional file systems fail? Key disadvantages.
Once upon a time in Smartville, a quaint and peaceful town renowned for its abundance of information, a predicament loomed over its residents. In this community, crucial records such as people's names, phone numbers, birthdays, books, and customer records were maintained chaotically in piles of paper and folders across various rooms, resembling a rudimentary file system. The citizens faced ongoing challenges. Obtaining necessary information required laborious searches through disorganized heaps of papers, with identical data stored redundantly in multiple locations. If alterations were made to one document, corresponding copies remained unchanged. This cumbersome system bred frustration among the townsfolk due to its slowness, complexity, and frequent inaccuracies. Enter Professor Edgar F. Codd, DBMS, a brilliant inventor who offered a transformative solution. "Allow me to reorganize your data into a cohesive relational database," he proposed. With magic of software-like precision, he built a revolutionary library. Every piece of data, whether a name, number, image, or otherwise, found a proper place within this new structure inside of computer with interaction software and hardware. Finding, adding, read, delete, or updating any information became quick and straightforward, and the need for redundant data storage was eliminated. Alongside this innovative development, Professor Edgar F. Codd imparted essential principles to the residents. Data is merely raw facts, e.g., John, 22, Mumbai. A database is akin to a methodically arranged library shelf, housing an organized collection of data. DBMS, the Database Management System, is a sophisticated mechanism or software for efficient data storage, management, and retrieval. In a metaphorical duel of systems, file system versus DBMS, the differences were stark. Storage. DBMS offers a central, organized repository compared to scattered random files. Duplication. DBMS avoids redundancy. Searching. DBMS expedites data retrieval. Data consistency. Maintaining consistency is facile with DBMS. Smartville DBMS reaped numerous benefits from the application of DBMS. Hospitals enhanced patient record management. Schools efficiently handled student grades and attendance. Banks ensured safe and accurate account information storage. Shops meticulously tracked inventory and billing. Professor Edgar F. Codd also introduced 3 impactful concepts. Data abstraction. Present users only the necessary information, preventing overload. Data independence. Alter storage methods without disrupting functionality. Database schema, a blueprint mapping the database's interior, akin to a building's floor plan. Further codifying his teachings, Smartville adhered to Dr. Codd's 12 golden rules for relational databases, emphasizing table-based data storage, access without complex coding, and support for data integrity, consistency, and security. The library was structured into 3 cohesive sections. User level, where people searched for data. Logical level, managing data interrelations. Physical level, the storage of actual files. In the rapidly evolving world of technology, understanding the architecture and data models of a database management system, DBMS, is fundamental for students embarking on the journey of computer science. This academic narrative is crafted to elucidate the concepts surrounding DBMS architecture, specifically the 2-tier and 3-tier models, alongside the data models, which include hierarchical, network, and relational models. To simplify this learning experience, imagine a classroom decked with dynamic visuals and flow diagrams, each meticulously animated to unveil intricate DBMS concepts in a format that is both comprehensive and engaging. Let us commence with DBMS architecture, which stands as the backbone for database management systems, providing the framework for data access. In the 2-tier architecture, the structure can be related to a banking application. Here, students can envision a direct connection between the user interface, perhaps your online banking app, and the database. The customer inputs data to check account balances or transaction history, which is sent directly to the database server, processed, and returned to the user with real-time information. It's akin to a smooth 2-step dance. Conversely, The three-tier architecture introduces an intermediary layer known as the application layer. Using a real-life analogy, consider an online shopping experience. A user places an order, UI. The application layer processes this request, verifying inventory, calculating prices, and only then communicates with the database. This middle layer enhances security and load distribution, thus reflecting a well-orchestrated three-tier sequence. Transitioning to data models, the hierarchical model can be visualized as a top-down structure similar to a folder tree within your computer. Each folder contains files, data, yet follows a singular path, much like a tree with branches leading back to a singular root. The network model broadens this analogy, presenting a web-like structure where data has multiple linked paths, akin to a social media network where users connect through various mutual ties, creating a more flexible, interconnected database framework. Lastly, the relational model, epitomized through table structures, aligns with the organization of household bills on a spreadsheet. Each table, relation, consists of rows, tuples, and columns, attributes, offering a simplistic yet powerful method to structure and query data efficiently. In crafting the animated explainer, ensure each segment is threaded with labels and arrows for clarity. The narrative should be laced with a lively voiceover, adeptly transforming complex facts into an accessible and interactive learning toolkit for high school and college freshmen. Ensuring this educational voyage into DBMS systems is both enlightening and enjoyable.